Okay, so thank you. So, because most of the lectures were on applied analysis, I would like now to give a lecture on discrete mathematics. And in fact, there will be a lecture on some theoretical background of image processing. If we would like to study uh, digital images, three-dimensional, we need to have some good definition of a Jordan surface. Jordan surface is some simple closed surface, which has the property that it's inside and also outside are connected, and also this surface is connected. So such surfaces then represent borders of object in three-dimensional pictures. Uh, the classical approach to this problem is using adjacency relations, but in this approach, we must always have at least two adjacencies, not only one. We must use one for the Jordan surface and another one for the complement. So it is a little bit inconvenient. For this reason, there was proposed a topological approach which uses only one structure, so-called Karimsky topology. It allows them to define Jordan surfaces. And I would like to propose another way how to define convenient Jordan surfaces, namely by using graphs. So here we have some basic concept of graph theory. I think everybody knows. I need not to repeat it. So like everybody knows what is path and walk and what is subgraph and so on and so on. Perhaps one definition which is not so common is the strong product of graphs. Of course, we have natural Cartesian or direct product of graphs. It is naturally defined, and but there exists also another product which has in fact more edges than the classical Cartesian product, because if we have this Cartesian product of vertex sets, then two vertices of this product are adjacent if not only the corresponding say coordinates are adjacent in the individual graphs, but they may also be equal, so that we have now more edges than in the classical Cartesian product. We will also employ the natural concept of tiling or tessellation applied to subset of z to the power of 3. Okay, so we will have a graph. As it was written, by a graph we mean undirected simple graph without loops, and we will denote by P sub n of G the set of all paths of length n in this graph G. Yeah? And now we will always work with some subset of this set of all graphs of length n. So we have some set of paths of length n. But if we have a subgraph, then the set of path inherited from this original graph in this subgraph is denoted by this way. Another important concept or denotation is this B star. If we have a set of paths of length n, then B star will be the set of all initial segments. What are initial segments? Initial segments are in fact finite sequences of vertices which are oriented which are initial parts of a path from B, but it may be oriented according to the orientation of this path, or just conversely. Yeah? You see here the exact definition. So this is set B star, and now we will define a B walk. B walk is quite easy to define. It is nothing but a sequence which may be which consists of initial segments. Yeah, so initial segments may be divided into initial segments, or it consists of initial segments. Yeah? This initial segment, this one, so on. So in this way, we define B walk. Now it is natural to use B walk to define a B connectedness. So we say that some set of vertices is B connected if any two elements of A may be joined by a B walk whose all elements belong to A. Yeah, connected means the first and last. The first is one point, and the last element is the other point. And then the maximal B connected set in G is called B component. Okay, and now we also say we extend our definition of a strong product of graphs also to paths. Namely, we may use the same philosophy to define a product of a set of paths. So if we have you know, we have say system of paths Bj, and then we define the product of this path in this way. Again, if this path consists of not only paths which are obtained when the corresponding coordinates of here are paths in individual graphs, but they may also be equal. You know? So the philosophy of this definition is the same like the philosophy of the definition of the strong product of graphs. And why we introduce this concept? Because of this proposition 5. If we have a system of graphs, and in every such a graph there is this set of paths Bj, and now if we have in every of these graphs some Bj connected subset, then the strong product of then the product of these subsets is connected with respect to the strong product of these paths in this strong product of graphs. Yeah, so that it's in fact say this strong product is closed under connectedness. So this is why we define these two concepts. And now we will switch to, this was quite such a general background, and now we will orient on some special graph with a special path set on this graph, and we will develop such a small theory concerning this individual graph. So we will focus on two adjacency graph on Z. Two adjacency graph is very easy. The two points are adjacent just if their distance is 1. Yeah. So this is graph H. And how to define the path set B sub n? B sub n, it was written somewhere before that n is a given positive natural number, yeah? Always. So this path set B sub n is defined here, but simply explained at this picture. Yeah? It's always this entuples. This paths are sequences of vertices starting from this vertex here and oriented according to this arrow. Yeah? So this is one path, another path from n to n, and so on. Yeah? So these are all paths. So we have now graph H and set of paths, and of course it may easily be seen that then this set Z is B1 connected, Bn connected, and which is interesting is that if we take n equal to 1, then the B1 connectedness is precisely the connectedness which is obtained by the Kalimsky topology, which is also sometimes used in image processing. Okay, so enough time. So now we now have graph H, on the vertex set Z, and we have this uh, uh, set of paths Bn. Now we now may apply now apply this strong product. So uh, we may construct a new connected structure on the digital space Z to the power of m. We will just take the strong product of m copies of the graph H, and the path, and this product will be the strong product of this path we introduced, this B sub n. So, or more precisely, we may consider for every positive integer a, we have this graph h to the power of m. Yes, this is a product of this graphs hj. Every hj equals j, and the path set will be this path set, which is also a strong product of bj, where bj is b sub n for every j. Now again it is easy to see that then the so-called digital space z to the power of m is b sub n m connected in this graph h to the power of m for every positive m. Okay, now again, if we take n equal to 1, then this connectedness b1 to the power of m in this graph h to the power of m, which is graph with the vertex set z to the power of m, coincides with the connectedness in the Karimsky topology on z to m, yeah? Because Karimsky topology is defined for z1, z to the power of 2, z to the power of n, for every m-dimensional digital space. And but the behavior of the Karimsky topology is well known, so we may restrict our consideration only to the situation when n is greater than 1. And of course, with respect to possible applications, the most important are the pictures which are two-dimensional or three-dimensional. So for us, the most important cases are when m equals 1 or m equals 3. In this situation, the graphs A2 and H2 and H2 to the power of 3, they are nothing but well-known 8 adjacency graphs on Z square and 26 adjacency graphs on Z to the power of 3. Yeah? So these are graphs which are well-known, very often used in image processing, these graphs. This path set B of n to the power of 2 is shown in this figure here. Look, yeah, this is the set of all of paths. Of course, there are also some paths which are missing between this path represented by this arrow and this path represented by this arrow. There are n-1 more paths, of course, yeah. Yeah, so it is on this figure. And now it is natural to call sets which are defined here to be cubes. We will call them fundamental cubes. Yeah, there are cubes with the length of every side to be 2n. Yeah, so it is in a natural way we define the concept of a fundamental cube. And now, using this cube, we may divide this cube always to two fundamental prisms. In fact, the exact definition of these fundamental prisms are given here. But to understand, look, if you have a fundamental cube, you may always cut it by a plane which is perpendicular to one face and which contains a diagonal. You will obtain two fundamental prisms. Yeah, and you may do it in fact in six ways. So you will obtain in fact 12 different fundamental prisms. And now, okay, we will cut again fundamental prisms. Namely, we may cut fundamental prisms in such a way that we will obtain three tetrahedra. We may do it in two ways. In this way, and the dual way. Here we cut. This is BB vertex, so we may cut off say C vertex. Yeah, so you see that there are two different ways. And now, yes, and each such uh, pre, uh, tetrahedra, each such a tetrahedron is called to be a fundamental tetrahedron. Yeah, so it is, the definition is somewhere here. Yeah, so it is here. So this fundamental tetrahedron is any of the three tetrahedra obtained by dividing a fundamental prism by the blah blah blah. It is just exactly written what is explained here on this picture. Of course, all these things are digital. Yeah? So this is this also these tetrahedra are digital. They are consisting of points of z to the power of 3. And which is important is that there is just a proposition which is used to prove the main theorem. And this is the main result of this talk, which is called digital Jordan surface theorem. If we have a subset of z square, subset of digital space, three-dimensional, if it is a polyhedral surface, such that the polyhedron it bounds can be face-to-face tiled with fundamental tetrahedra, then the induced subgraph z squared minus s of h to the power of 3 has exactly two components. It means two components, such that one of them is finite. It is in fact inside component, and the other is infinite, outside component. And the union of each of them with S is connected in this space. So it is the main result which defines digital Jordan surface. So it is just to demonstrate this result. We have here such a picture of surface which is boundary surface of a digital right square bipyramid or octohedra if you want, and the surface satisfies the condition of theorem 3-4. Hence, it is a digital. This surface of this octahedron is Jordan surface with respect to this connectedness. You see that it consists of this of the 16 fundamental tetrahedra. 16 fundamental tetrahedra are this octahedron is obtained by tiling them. Huh? So it is, but of course we may find many other examples. So that's in fact also to make a conclusion. We found a definition, convenient definition of Jordan surface, which may be used in digital image processing, which may replace the Karimsky topology, because Karimsky topology its using is restricted because it doesn't allow some complicated surfaces. The surfaces may, for example, never turn under the angle less than p halves. So, but with in this way, this our proposal is better than Kalinski topology. Okay, so perhaps it's all I would like to tell you. So thank you for your attention.